All right, welcome. In this video, I'm going to be telling you about Descartes' rule of signs. Okay, and while this is not going to be the most important thing you learn about in my Algebra 2 class, it is good algebra, and this is a bonus topic because if you're in my section, you're going to learn about Descartes' rule of signs because I think it's a little bit useful, and I think it helps us understand a little more context about the rational root theorem. Let's get to it. All right, so what the theorem says is that the number of positive real zeros, like roots of the polynomial that are real numbers and are positive numbers, is equal to the number of sign changes in the coefficients of the polynomial, or fewer by a multiple of 2. Now, you just learned about complex conjugates theorem, and if it's fewer by a multiple of 2, it's because that multiple of 2, those are imaginary roots that pulled away from your potential positive solutions. Okay, the number of negative real roots of a polynomial is equal to the number of sign changes in the coefficients of f of negative x, or fewer by a multiple of 2. And at this point, you're watching this video, I'm going to assume you don't really know how to do this, and I'll kind of show you how when we're going and doing it. But I'm just going to show you how this works and kind of tell you about how this is something that you can use to narrow down possibilities when you have to use the rational root theorem to guess roots. Okay, so it kind of, if you don't use Descartes' rule of signs and all you have is rational roots, it's like, okay, well, what if my constant term is something like, 56 or something that has like a whole lot of factors? And it's like, yeah, that is tough, isn't it? But this is something that can help, and it used to help back before there was calculators. So f of x is 1x to the 3 plus 1x plus 1. Okay, so I've got positive, positive, positive. I would say f of x has no sign changes. Okay, if f of regular x has no sign changes, well, that's the number of positive real roots. So that means it's got no positive real roots. Okay, and now I'm going to check f of negative x. Okay, so this is where I'm going to just show you what I mean by that. Okay, so I'm just going to, instead of x, I'm going to be plugging in negative x. Okay, so just everywhere I see x in the formula for f, I'm replacing it with negative x and parentheses around the negative x, because you need to be careful. Always got to be judicious with those parentheses. So I'm going to take, I did cube x, now I'm going to be cubing negative x. Okay, then I added x, but now I'm going to be adding negative x, and then I added 1. Okay, so wherever I saw an x in the formula, I'm replacing that with negative x. And now, negative x to the third power, it's like, 3 copies of negative x. So it's 3 negatives and 3 x's. And we know that an odd number of negatives multiplied together does make a negative. So I'm going to have negative x cubed plus a negative x, so that's minus x plus 1. Okay, I went minus, minus, plus. Okay, minus to plus, that's a sign change. Okay, I'm going to say f of negative x has 1 sign change. Okay, we saw it right there. That means that there is exactly 1 negative real root. Okay, so this doesn't have a lot of possible rational roots, but say that was 24 or something. We know that we don't even need to bother testing the positive numbers, right? Okay, that would knock our choices in half. Okay, or if you know there's only one, say there's 1 negative real root and you already found it, you don't have to keep looking. Okay, that was kind of what it used to be good for in the past. Okay, now for us, we're not going to really use this all that much, but I can tell you that, hey, I know how this one's going to play out. This f of x, this is going to have 1 real root, because it's got 1 negative real root. It's got no positive. Other 2 have to be complex. Imaginary. They are complex, but all numbers are complex. So, third degree polynomial, I'm expecting 3 roots. I've got 1 negative real root, and then that tells me I have 2 non-real imaginary roots. Let me look for one other good example for how we can classify all the possibilities for a given polynomial. Okay, I was just looking farther along the notes. I see where it's going. I like what I've written out. Okay, so g of x, I'm going to just consider the sign changes on g. I've got 1 sign change from positive to negative, but then it's negative the rest of the way through. Okay, so g of x has 1 sign change. that means to me that g of x has one positive real root. Okay. I'm going to consider g of negative x. Okay. So that's going to be g of negative x equals x to the fourth. So it'll be negative x taken to the fourth power minus 2 times negative x squared minus negative x minus 1. Okay, now if I plug in negative x everywhere I saw x before and was careful about my parentheses, okay, I'll have this. And if I take negative x to the fourth power, that's negative 1 to the fourth, which is 1, times x to the fourth. It's another way of looking at it. That's going to be positive x to the fourth, okay, because of the even power. Okay, minus 2 times negative x squared. Well, if I multiply negative x times negative x, that's positive x squared. So I've got negative 2 times positive x squared minus a negative x minus 1. Okay, this one has got 1, 2, 3 sign changes. Okay, so I'm going to say, okay, 3. Okay, so g of negative x has 3 sign changes. Okay, so this is going to give us like kind of a variety of possibilities. So I'm going to make a little table plus positive, minus negative, and imaginary. And we'll kind of just fill out some possibilities. Okay, now we know there's always going to be just one positive real root. But if g of negative x has 3 sign changes, that means that there's 3 negative real roots, or fewer by a multiple of 2. I didn't even mention it. It could be fewer by a multiple of 2, but it's like, oh, you can't have negative 1 real roots. That makes sense. Okay, but I could have or 1 negative real root. In that case, 2 of them would kind of go over to the imaginary side. Okay, so maybe I've got 3 negative real roots. In that case, I've got all 4 of my roots accounted for. I have no imaginary roots. If there was one of each, 1 positive and 1 negative, then I would be left over with 2 imaginary. But I don't have any other possibilities, right? Because this is the only possibility for positive real roots. These are the possibilities for negative real roots. Okay, so I've hit them all. Okay. Now these are kind of getting at, like, well, is this catch everything? And it doesn't quite catch all of them. And this one caught the video pause looking for a good example. It's like, well, what is going on here? Does Descartes' rule of signs, does it not fully work? Don't worry, it does fully work. I was just having doubts when I shouldn't have. X to the fifth plus x, there's no sign change, plus plus. Okay, so h has, let me get the previous example off screen for you. And I think I might zoom in also. Yeah, that'll be good. Okay, so h has no sign change. Okay. Oh, I need h of negative x. H of negative x equals negative x taken to the 5th power plus a negative x. Okay, and if you take a negative x to the 5th power, you're going to get negative x to the 5th because of the odd degree there, and then a minus x. H of negative x also has no sign change. So that means there's no positive roots or negative roots. That's concerning, right? Because this is a 5th degree polynomial with a positive leading coefficient, meaning as x approaches negative infinity, I'm going down. As x approaches positive infinity, I'm going up, right? So I've got negative values of h, positive values of h, and h is a continuous function because it's a polynomial, so it's got to be equal to 0 somewhere. There's got to be an x-intercept. Every odd degree polynomial has at least one intercept. And then you realize, oh, hey, it's right there at x equals 0. Okay, so I don't really know how Descartes' rule of signs interacts with 0 roots, but I can see that x equals 0 is a root. I know there are no positive or negative roots because of the analysis, the Descartes' rule of signs analysis I did. So that must mean h has 4 imaginary roots. And then x to the 4 plus x to the 3, I need to focus that a little bit better. don't know if that's improved. I hope it is for your sake. X to the 4 plus x to the 3, you know, okay, so f of x has no sign change. Okay. Okay, I forgot what I was going to say about that. It means no positive roots, whatever. F of negative x equals negative x taken to the 4th power plus negative x taken to the 3rd power. Okay, if I take negative x to the 4th power, I'm going to have positive x to the 4. If I take negative x to the 3rd power, I'll have negative x cubed. That's one sign change. Okay, and that means, okay, now I know that there's one negative root, no positive roots. It's a 4th degree polynomial. What's going on here? Okay, and what it is that it's just one x-intercept, and I think it's going to be a triple root. Wait a second, hold on here. Oh no, it's not. X equals 0 is a triple root, and x equals 1. Oh wait, no, pardon me. X equals negative 1 is going to be a single root, is what's going on there. Okay, so this one was a little ambiguous. But that's the Descartes rule of signs. Thanks for watching this video. I really appreciate it. You know, you show that you're extra dedicated by your commitment to learning all of the things that we could possibly learn in our Algebra 2 class.